Okay, so the first thing we're going to do is we know this is our induction hypothesis is this. And so for our basis, the first thing we're doing is we want to do the first case. So we're going to say the first case is just k equals 0. So just one case, k equals 0, and then n equals 0. So we're just doing 1. So 2 to the k is equal to 2 to the n plus 1 minus 1. So we're going to say here 2 to the k, this means 2 to the 0. I'm just bringing, if I were to plug this in, I'm just having one term in the sequence. There's no additional terms for the sum. So then if I plug in 2 to the n plus 1, I'm plugging in what n is, or what this is in here. So this is going to be 0 plus 1 minus 1. And so what I'm trying to show is that this term works, that we get this answer, right? So this closed form of the equation is the same as my sum over here on the left-hand side. And so 2 to the 0 is 1. And we know that 2 to the 0 plus 1 is 2 to the 1. So this is what we're trying to do. Like, is this true? Is this true, right? So 2 to the 0 plus 1 is 2 to the 1 minus 1. And so 1 is equal to 2 to the 1 is 2. So 2 minus 1 is 1. So that means it works. Okay, and so what we're doing with induction proofs is we want to show that the base case just for one, that it works. So the easiest thing to do is just to do one term from our sum. So that's what we're doing when we say k equals 0 to n equals 0. That's just one term, the first term, and that's the only thing we're testing. And when we take the first term of this sequence, we just have 2 to the 0. That's the only term we have because n doesn't go any higher than 0. And then this side on the right is the closed form equation. So this whole sum is equal to this closed form. So we want to check and see, does it work for the easiest only one term of my sum? And it does. So then the next thing we want to do when we do the induction step, we must show that like any term will work. And so that's the idea of the n plus 1. So it's saying I can go up to n, right? But can I go more than 1? Can I go more than n? Can I add the next term? Does that work, right? And so we know this is 2 to the k is equal to 2 to the n plus 1. So I'm plugging in. Before up here in my assumption, I had to just 2 to the n, and I get this closed form. Well, now what if I have n plus 1? I now need to plug in for the n here, n plus 1. So that's my 2 to the n plus 1 and then plus 1. So all I've done is I've taken, this used to be n, and now it's n plus 1. So I'm plugging that in here into the closed solution, minus 1. And so what I want to know then is, does the left side equal the right side? Does this sum, right, equal the closed form? And how do I tell that? Well, I know that n plus 1 from k equals 0. So thinking about the sum of 2 to the k. Well, what do I know? I know that I can write this as k equals 0, a sum to n, right? So all I've done when I have to n plus 1 instead of n is I just have added one more term. So I can say, okay, I know that's the old 2 to the k, but I need to add the next term, which is just 2 to the n plus 1. So this is made up of the sum to n plus the next term. So this is the next term. Okay, and so what I want to know then is, so I'm going to take this side of the equation and I'm going to represent it by this. So what I'm going to try to plug in here, I'm going to plug in this right here and then set it equal to this, the closed form, and see if I get the same answer out. And if I do, then I know that it works for any. I'm saying that if it works for the next item in my sum, then it's going to work for all items in my sum. That's what induction is about. So I'm taking this and I'm going to set this side equal to this side by plugging this in, by taking this and plugging it into here. So that's what my next step is going to be. So I'm going to write to the n, 2 to the k equals 0, plus 2 to the n plus 1, right? So that's, I'm just plugging in for that. And is that equal to 2 to the n plus 1 plus 1, and then minus 1? Okay, well, I know this is my original assumption, right? This is back up here at the beginning, my assumption, this. So I can plug this part in for this down here. So all I'm doing is I'm taking the closed form and I'm plugging it in here. So I know this is 2 to the n plus 1 minus 1, right? And then this is the next term, the n plus 1 term, so plus 2 to the n plus 1. Does it equal 2 to the n plus 1 plus 1 minus 1? Does it equal it? Well, let's check. Well, we see 2 to the n plus 1 and 2 to the n plus 1 here, so I can factor those. So I get 2 times 2 to the n plus 1 minus 1. And does it equal 2 to the n plus 1 plus 1 and then minus 1? Well, 2 times 2 to the n plus 1, well, that's the same as I'm just adding 1. It's like 2 to the n plus 2, right? It's just another term that goes in here, minus 1. Does it equal 2 to the n plus 1 plus 1 minus 1? Does it equal it? Well, this is the same, right? So 2 to the n plus 1, or 2 to the n plus 2 minus 1 equals, when I say 2 to the n plus 1 plus 1, that's just 2 to the n plus 2 minus 1. So this side, left side, is equal to the right side. So it works.